Welcome to the Deep Dive. We're the place where we dig into complex research, pull out the key takeaways, and basically make you instantly well-informed.
That's cool.
And today we are plunging into a really groundbreaking study. It's from a Nature Portfolio journal, and it could seriously shift how we think about climate intervention.
Yeah, it's pretty significant stuff.
Because, let's be honest, climate change is this huge, urgent reality, right? And we're all struggling globally to hit those warming targets. It's daunting.
Absolutely. And while cutting emissions is, of course, #1 priority,
It's paramount, yeah.
scientists are looking at other ideas. And this new approach to managing solar radiation, well, it's a bit of a head turner.
A game changer, possibly, offering a surprisingly efficient path.
Potentially. That's what we're digging into. Our focus is this paper, Stratospheric Aerosol Injection Can Weaken the Carbon Dioxide Greenhouse Effect. It's an innovative modeling study proposing a method that really challenges conventional thinking on solar radiation management.
Okay, so our mission for this deep dive is clear. We're going to unpack the science, understand this novel mechanism,
Right.
compare it to the usual method,
Sulfate approach, yeah.
and explore the really fascinating, maybe sometimes concerning implications of, tweaking the climate like this with such precision.
Exactly. So you walk away knowing the critical stuff from this cutting-edge research.
Let's dive in. So to really get why this is such a big deal, we need to set the stage, right? The challenge.
A huge challenge, keeping warming below that 1.5 degrees C Paris target.
And despite all the efforts, emissions are, they're still going up.
Unfortunately, yes.
Yeah.
And that reality is pushing researchers to look harder at, alternatives, plan B, C, D, including solar radiation management or SRM.
And SRM usually means stratospheric aerosol injection, or SAI. That's the main one people talk about.
Right. And the conventional thinking for SAI, the standard model, involves putting tiny reflective particles, think sulfur dioxide, which turns into sulfate aerosol.
Under the lower stratosphere, correct?
Correct. Lower stratosphere. Maybe 20 kilometers up, something like that.
And it acts like this giant engineered sun shield. These little particles bounce sunlight back into space, increasing the Earth's albedo, its reflectivity.
And that cools the surface. We see it happen naturally, too.
Right. Volcanoes, big eruptions shoot millions of tons of SO2 way up there,
creating that sulfate layer, and bingo, the planet cools down for a bit. Maybe a year or two. It's a proven effect. Temporary, but proven.
But, and this is the big but, isn't it? That conventional way.
It has a major limitation.
Yeah, it cools things down, but it doesn't actually fix the root cause.
Exactly. It doesn't touch the rising greenhouse gas concentrations. It's like putting a bandage on the symptom, not curing the disease. It just masks the warming. It can't directly cancel out the radiative effect of all that extra CO2.
And this is where the new study gets really interesting. It flips the script. Instead of just reflecting sunlight, what if you could actually mess with the greenhouse effect itself, make it weaker?
That's the core idea. This novel approach uses a totally different kind of aerosol, absorptive ones, like black carbon, soot, basically.
Okay. Absorptive, not reflective, and they put it somewhere else.
Yes. Crucially, they propose putting it much higher up, into the upper stratosphere. We're talking maybe 30 kilometers, around 10 hectopascals pressure level.
And here's the kicker, the kind of aha moment in the paper, right? The idea is these black particles warm a very specific layer way up there.
Exactly. They warm the layer where CO2 normally radiates heat out to space most effectively. It's technically where the CO2 absorption bands reach unit optical depth. Think of it as the altitude where CO2 has the clearest shot at sending infrared energy outwards.
So it's super sensitive to temperature changes right there.
Extremely sensitive. And by warming that specific layer, the whole process enhances the total amount of infrared heat escaping Earth.
Wow, so you're directly weakening the greenhouse effect.
Precisely. Without changing the CO2 levels themselves. It's a completely different physical mechanism than just reflecting sunlight.
Which is a big deal. Most SAI ideas are all about reflection, sulfates, lower stratosphere. This black carbon absorption upper stratosphere. It hadn't really been tested properly in complex models, had it, for this specific purpose?
Not really in coupled ocean atmosphere models, no. There were studies on black carbon, sure, but mostly focused on, potential surface cooling effects lower down, not this idea of tweaking the greenhouse effect by changing the temperature structure way up high. It's a fundamental rethink.
Okay, so let's get into why this works. You mentioned the temperature structure.
Right, because the strength of the greenhouse effect isn't just about how much CO2 or methane is up there. It also really depends on the temperature profile of the atmosphere, especially vertically,
And the upper stratosphere is the key place
because that's where CO2 does its most effective radiating to space, where it hits that unit optical depth. So any temperature tweak right there has the biggest possible bang for its buck in terms of changing the outgoing heat. It really is the sweet spot.
the study actually shows this sensitivity, right? Like warming higher up has a bigger impact.
Yeah, they demonstrate that. The same amount of warming has a much larger effect on outgoing long-wave radiation if it happens higher up, especially if it lines up perfectly with that CO2 emission level. That's where you get the maximum sensitivity.
And just to be clear, this isn't about changing radiation in a CO2-free sky. It's about modifying how CO2 itself interacts with heat.
Exactly. It's modulating the CO2 greenhouse effect. Warming that upper layer just makes it easier for the heat trapped by CO2 to escape.
Okay, let's talk efficiency then. How does this black carbon idea stack up against the standard sulfate aerosols in the models? And we should stress, these are idealized models.
Very important point. Highly idealized simulations. They don't have all the real-world messiness, interactive aerosols moving around, complex chemistry, how you'd actually do it.
Yeah.
But they're good for isolating this physical mechanism.
Got it. So sulfates first. How do they perform in the models?
With sulfates, the cooling effect, the ERF, or effective radiative forcing, it doesn't really matter that much exactly where you put them vertically in the stratosphere. It's pretty consistent.
And the relationship between amount and effect?
Roughly linear. More sulfates, more cooling. They found like 0.5 teragrams, that's 500,000 metric tons, gives about 0.12 watts per square meter of cooling. 10 times that, 5 teragrams, gives about 1.3 watts per square meter. Predictable.
Okay. Now, black carbon.
Totally different story. The ERF is highly sensitive to altitude. Put it in the wrong place, not much happens. Put it way up high.
Yeah.
And the peak cooling effect they found, around 2 watts per square meter, happened at the two highest levels they tested, near 30 kilometers. And here's the kicker. That cooling effect was roughly an order of magnitude larger than what they got from the same mass of sulfates.
Wait, say that again? An order of magnitude?
Yep. Comparing 0.5 teragrams of black carbon way up high to 0.5 teragrams of sulfate lower down the black carbon was about 10 times more powerful, mass for mass.
Wow, that's huge. And that's mainly because of that long-wave radiation effect, the enhanced heat loss.
Primarily, yes. It's driven by that warming of the CO2 emission level, boosting the infrared heat escaping to space. The bottom line from the study: put black carbon in the upper stratosphere, and you get much more efficient cooling per unit mass, about 12 times stronger than conventional sulfate approaches.
12 times. Incredible. And you mentioned it works differently too. Mostly long wave for black carbon, mostly short wave reflection for sulfate.
Exactly. For black carbon, over 2/3 of that altitude-dependent effect comes from the long wave part, changing heat leaving. Sulfates barely touch the long wave. They're all about reflecting sunlight coming in. Plus, black carbon itself is just better at blocking radiation generally, about 3 times more effective per unit mass than sulfate, because it absorbs light strongly, which sulfate doesn't really do.
Okay, so if these numbers translate to the real climate, what does it mean for things like temperature, rain, atmospheric circulation? The models simulated this too, right?
They did. They ran coupled simulations using amounts that gave roughly comparable cooling, 0.5 teragrams of black carbon versus 5.0 teragrams of sulfate. Both placed high up for effectiveness.
And the cooling result?
The black carbon actually induced slightly more global cooling, about 0.8 degrees Celsius, compared to about 0.6 degrees for the 10 times larger mass of sulfate. It just reinforces that efficiency point. Black carbon packs more punch per kilogram.
What about rain precipitation?
Well, more cooling generally means less evaporation, so less rain globally. Both methods reduce rainfall, but the black carbon caused a greater reduction.
Okay, that makes sense.
But here's something odd. They saw what they called a fast precipitation decline with black carbon. Rain decreased quickly, even before the surface temperatures really dropped significantly.
That's counterintuitive. Didn't some people think upper stratospheric warming might increase rain?
Some initial thoughts, perhaps, yeah. But the model suggests otherwise here. Their preliminary looks suggest it might be due to some weird infrared absorption effects lower down in the troposphere, maybe linked to unexpected water vapor increases there. It just shows how complex these knock-on effects can be.
Right. And the patterns of change. Where does it get cooler or drier?
Both methods showed delayed cooling over the Southern Ocean. This creates a contrast, more cooling in the northern hemisphere than the southern.
Okay.
But the black carbon simulations showed a stronger contrast, plus more pronounced Arctic amplification. The Arctic cooling faster than elsewhere, and the cooling over the northern Pacific was more uniform. so different spatial fingerprints.
And precipitation patterns.
A general drying trend, kind of the opposite of the usual wet gets wetter, dry gets drier thing we expect with warming. They saw pronounced drying in the tropics and some wetting in the subtropics.
And
It showed even more uniform drying across the tropics. The fact that these tropical patterns were consistent across models suggests the radiative forcing itself is really driving those particular changes.
So we've got this picture of higher efficiency but different climate responses, which inevitably brings us to the downsides, the potential unintended side effects. Because messing with the stratosphere like this, it's bound to have risks, right?
Absolutely. And the study highlights some key ones. A big one is warming the tropopause, that boundary layer between the lower atmosphere and the stratosphere.
Both methods do that.
Both do. But black carbon, because it absorbs so much more energy, causes substantially greater warming there.
And why is warming the tropopause a problem?
Well, a warmer tropopause can let more water vapor leak up into the normally very dry stratosphere.
The freeze-drying effect gets weaker.
Exactly. And more water vapor up there is potentially bad news for ozone. Higher temperatures already speed up ozone-destroying reactions, and water vapor itself acts as a catalyst for ozone depletion. So it's double whammy, potentially. They also saw less humidity and fewer clouds in the upper troposphere in the models. Significant changes.
What about the big atmospheric circulations, like the Brewer-Dobson circulation that moves air and ozone around?
That's another really interesting difference. Sulfates are generally expected to speed up that circulation, but this study suggests the intense heating from black carbon might actually slow it down.
Slow it down, what would that do?
It could really mess with how ozone is transported from the tropics to the poles. You could end up with less protective ozone over mid-latitudes, for example. It changes the whole distribution pattern.
And the polar vortex, that winter whirlpool of air over the poles.
The black carbon heating, especially at seasonal variations, might actually strengthen the temperature difference between the equator and the pole in winter. That could lead to a stronger, more stable polar vortex.
Which sounds good, maybe. Less cold snaps.
Not necessarily.
Right.
A stronger vortex can affect how the stratosphere and troposphere interact, which influences storm tracks, jet streams, and ultimately weather patterns over places like Europe and North America. It's complex.
And we need to remember the models used here have limits, right?
Definitely. They pointed out their models lacked interactive stratospheric chemistry, so the ozone effects are inferred, not fully simulated, and the model top wasn't super high, which can limit how well they capture some of these dynamic effects. More sophisticated models are needed.
Are there other worries with this black carbon idea?
Yes. Aerosol sedimentation is one. These black carbon particles won't stay at 30 kilometers forever. They'll eventually drift downwards.
And as they fall?
They could start warming the lower stratosphere. That would counteract the cooling effect somewhat, reducing efficiency. And warming the lower stratosphere could also let more water vapor in, again, potentially worsening ozone loss and offsetting the cooling.
And what if they fall all the way down onto snow or ice?
That's a big concern. Black carbon landing on bright surfaces like snow or ice drastically reduces their reflectivity, their albedo. They absorb more sunlight, which accelerates melting. So you could inadvertently warm the surface in sensitive regions, offsetting the intended global cooling.
Any potential upsides to these side effects? Anything unexpected?
Well, one interesting point, they noted black carbon is also good at absorbing ultraviolet, UV, radiation. So potentially, the aerosol layer itself could shield the surface below it from some harmful UV. Might even locally reduce ozone depletion below the layer itself, but again, not fully quantified, needs more study.
Okay, so clearly it's a fascinating mechanism, but tons of complexity and unknowns, which brings us squarely to the study's limitations and what needs to happen next. These were idealized experiments.
Hugely important to keep stressing that. They didn't include aerosols settling out realistically, complex air movements carrying them around, interactive chemistry changing them, their actual lifespan, how they might clump together, or even effects like self-lofting, where absorbing aerosols heat the air around them and rise higher. None of that real-world detail was in these initial tests.
Which means we can't just take these results and run with them.
Absolutely not. These findings scream for more research. We need to know if it's truly feasible, how effective it would really be, and crucially, map out all those potential risks and side effects properly.
Using better tools.
Yes. The authors call specifically for studies using much more comprehensive models, Earth system models that include detailed atmospheric chemistry, aerosol physics, dynamic oceans, the works. We need to understand all the interactions, optical, chemical, photochemical, plus how these particles actually move, how long they last, how their size changes over time.
And then there's the small matter of actually doing it. getting stuff up to 30 kilometers.
Yeah, the engineering challenge is immense. Current high-altitude aircraft mostly top out around 20, maybe 25 kilometers for specialized ones. Getting payloads routinely and continuously to 30 kilometers or higher is, well, it's a whole different ballgame.
What options are there?
The paper mentions things like rockets, maybe specialized cannons, firing payloads up, high-altitude balloons, but none are easy or cheap for the kind of sustained deployment you'd need.
And even if you could get it up there, operating such a system.
Huge operational hurdles. You'd need continuous delivery, ways to adapt the deployment based on atmospheric conditions, constant monitoring, a whole new infrastructure, and this is critical, some kind of international agreement and coordination. You can't just have one country doing this kind of thing unilaterally.
So let's wrap up our deep dive today. We've uncovered this really distinct physical mechanism for climate intervention using absorptive black carbon aerosols way up in the upper stratosphere.
And the headline finding is that it could, theoretically, weaken the greenhouse effect much more efficiently, maybe 12 times more, mass for mass, than the conventional reflective sulfate approach.
But, and it's a huge but, it comes with its own unique set of climate impacts, different patterns of cooling and drying, and a whole suite of potential side effects, particularly around stratospheric temperature, water vapor, ozone, and circulation, that are very different from the sulfate risks, and many are still poorly understood.
It really is a fascinating, and you said it earlier, provocative idea. It opens up completely new lines of research and forces us to think about climate intervention in a different way.
Absolutely. And it leaves us with a really important question for you, the listener, to think about. If we could develop the power to directly tweak the stratosphere's temperature like this, to fine-tune how much heat Earth radiates, what are the immense ethical and governance responsibilities that come attached to that power, especially given these complex, potentially serious, and quite distinct side effects on global climate and chemistry? What new questions does exploring this possibility raise for you about our planet's future and how we manage it?